So the next speaker is Jawad Haj-Yahya. He received his PhD in computer science from Haifa University in Israel. He also worked for Intel for many years as a processor architect. And while there, he received the Intel Achievement Award, the highest award that Intel gives out for significant contributions to Intel processors. Jawad is now a senior researcher at ETH Zurich, leading multiple projects on energy efficient computing and hardware security. Jawad, take it away.
Yeah, thanks, Radu, for the introduction. Sorry, I was muted. So can you see my slides?
Yes.
Okay, so my name is Jawad Haj-Yahya and I represent IChannels. So in many recent processors, CPU cores share the same voltage regulators and the clock domain, which are controlled by a central power management unit. The relationship between load voltage, VCC load, supply voltage, VCC, and current, ICC, under a given system impedance, R load line, is VCC load equal VCC minus ICC times R load line, as also shown in the following figure. So the power management unit adds a voltage guardment to VCC to a level that keeps VCC load within limits, above the minimum functional voltage VCC mean under the most intensive load power virus with current ICC virus, and below the maximum operational voltage VCC max under the lightest load leakage with the current I leakage. Prior works propose covert channels that exploit some of the throttling side effects of executing power-hungry instructions. These works are limited and use inaccurate observations. Our goal in this work is to firstly experimentally understand the throttling side effects of current management mechanisms in modern processors to gain several deep insights into how these mechanisms can be abused by attackers. And secondly, build a high-capacity covert channels, IChannels, between otherwise isolated execution contexts. Then finally, practically and effectively mitigate covert channels caused by current management mechanisms. We experimentally study three modern Intel processors, Haswell, Coffee Lake, and Cano Lake. We measure voltage and current using a DAC acquisition card in IDAC. And our rigorous characterization on real system provide deep insight on current management mechanisms. We find that firstly, the core frequency reduction that directly follows the execution of PHIs at turbo frequency is due to maximum instantaneous current limit and maximum voltage limit protection mechanisms. Secondly, power gating AVX execution units accounts for only about 0.1% of the total throttling observed when executing PHIs. Most of the throttling time is due to voltage transitions. Then current management mechanisms result in a multi-level throttling period depending on the computational intensity of the PHIs. And finally, the 4 times a core IPC reduction that directly follows the execution of PHIs is because the core blocks the front end to the back end UOP delivery during 75% of the time for both threads in SMT core. We built 3 high throughput covert channels between sender and receiver that exploit throttling side effects of current management mechanisms on the same hardware thread across SMT threads and across cores. Each covert channel can send 2 bits from sender to receiver in every transaction. I'll present only the third covert channel, ICC cores covert established across different physical cores. So ICC cores covert channel exploits the side effect of multi-throttling cores. And this side effect, when 2 cores execute PHIs at the same time, The throttling period are exacerbated proportionally to the computational intensity of each PHI executed in each core, as illustrated here. So T0 and T1 in core 0 and core 1 start executing instruction 0 and 128 bit heavy loop, both with IPC of 1. T0 and T1 loops are throttled. Once the T0 target VCC is reached, T0 throttling is stopped. T1 continue to be throttled since the PMU will not handle T1 voltage transition until T0 voltage target is reached. So T1 throttling period depends on the computational intensity of N0, which determines the VCC level to which the PMU needs to increase the supply voltage before handling T1's voltage transition. The sender executes a PHI loop with a computational intensity level depending on the value of two secret bits it wants to send. Then the receiver can infer the 2 bits sent by the sender based on the measured throttling period of the 128 bit heavy loop. And we evaluate iChannels on Coffee Lake and Cannon Lake. Our workloads are proof of concept codes of the Covert channels. We compare iChannels to 4 recent works, and we propose practical 3 mitigation mechanisms. So please see our paper for more details. We compare ICC thread Covert against NetSpectre. The NetSpectre Covert channel can send 1 bit per transaction on the same hardware thread, while our ICC thread Covert channel can send 2 bits per transaction. We compare ICC SMT Covert and ICC Cores Covert against DFS Covert, Turbo CC, and PowerT, the related works that build Covert channels across SMT threads and cores. ICC SMT Covert and ICC Cores Covert throughput is up to 145 times that of recent works. So we introduced iChannels, new Covert channels that exploit current management mechanisms in modern processors. We showed that multi-level throttling effects of current management mechanisms can be exploited for malicious information leakage on real systems. And iChannels is 2 times and 24 times higher throughput than existing state-of-the-art channels, Covert channels. We propose multiple practical mitigations to protect against iChannels in modern processors. And we hope that our work paves the way for eliminating the confidentiality breaches such current management mechanisms lead to. So thanks for your attention. I'll be happy to take questions.
Thank you, Jawad. This is quite an interesting way to use current throttling. Let me see if we have any questions. Please post your questions in the chat. I'll get us started by asking a clarification question, perhaps. Do you need to start at always be at turbo level before you can induce a transition or a voltage transition? Or essentially, is this dependent on the baseline voltage at which you start? Let's say you're operating in some lower power mode.
Yeah, the unique thing about our Covert channels compared to some of the previous works is that it happens in every like in every frequency, so it does not have to be turbo.
Does not have to be turbo. Okay, very good. Let's see. I have a question here from the chat. Can you verify? How can you verify the underlying mechanisms that lead to the Covert channel?
Oh, actually, we in our paper there is a detailed characterization process that we did. I just presented here like the major findings of this process. And basically, we did a characterization for the processor, and we see, like in the paper, you can see how we figure out how the ICC max protection and the VCC max protection works. And also the throttling itself, like prior works say, for example, that the throttling is happening due to frequency reduction four times. This is what I presented here in the conclusions. But actually, the throttling is happening in the pipeline once the core is blocking the front end to the back end. And we show the method how to reverse engineer this all of our findings.
Okay. Can SGX or other enclaves mitigate this power covert channel?
Yeah, actually, SGX cannot do that because this is a mechanism inside the power management, and it can happen in every time that you execute power hungry instructions, which is basically AVX instructions and different, or AVX3 or like basically AVX 128, AVX 256, and AVX 512. And it depends also on the type of the instructions. So we call in the paper, you can see the details. We call some instructions heavy and some instruction low, and depends on the type of the instruction. All of this we call the intensity of the instruction. So it depends on these factors. Yeah.
Okay, let's see. There are no more questions in the chat. I do have one or two more so how dependent, I guess this is a multi-part question. How dependent is this channel on the architecture or the type of voltage regulator used? So for instance, I assume you're communicating cores have to share a voltage regulator, correct? If you have per core regulation, I assume this will not work, correct?
Yeah, actually, this is a very good question. Like we talk about this in the paper. Actually, one of the mitigations for one of the covert channel is to have a dedicated voltage regulator, and it can mitigate some of the issues there. But we also talk about the limitation of having a per core voltage regulator for some of the covert channels. So for example, also we talk in the paper that Haswell processor, for example, that one of the processors that we characterize, and we see the covert channel that NetSpectre talk about, and our first covert channel, which is ICC thread covert, it's still there, and the per core voltage regulator can mitigate part of the latency because the integrated voltage regulator is faster than the off-chip voltage regulator, but it cannot mitigate. It cannot fully mitigate this covert channel. We propose other methods to mitigate this.
Very good, very good. Thank you, Jawad, very much for your presentation.